Hi guys, this is Ken Delcor. I'm going to go through a little bit of a lesson on Introductory to Hydronics. I am excited about this chapter as it's a really fun one to do. Let's get into it. So in our first section that we're going to go through for you guys is going to be just really kind of an introductory to just understanding the properties of water and some of its characteristics, maybe why they use it, and also some of the maybe some of the downsides of using water. So let's take a look at it. So we'll take a look at those things. We'll take a look at the relationship between water and also pressure in the system. So one of the facts that we'll hit up on initially is going to be the fact that water is comprised of hydrogen, oxygen, and one of the things about the fact that it has hydrogen and oxygen, it has certain specific characteristics within that compound that are kind of good and also kind of bad. One of the characteristics of water that we recognize and that we know is that water generally freezes in its pure form. It freezes at 32 degrees Fahrenheit. When water is, and it boils at sea level at 212. Now we're going to talk about specifically, that's not very high for some systems. We may have to have that increase. So we'll talk a little bit about that. Another area of water that we're going to look at is essentially the fact that water has a weight of about 62.41 pounds per cubic foot. That's what we call its density, and that is standard density at roughly 32 degrees Fahrenheit. So, and we'll look at that a little bit. Now, one of the things that is interesting, the fact that water has a different density at 212 degrees Fahrenheit, that it actually decreases. So we'll look at that. Obviously, higher temps, lighter weight. We'll talk about the reasoning and what goes on with that. And primarily the reason why the density does decrease is the fact that the water is expanding. Those molecules are getting bigger, so you actually have less of that fluid in that same space, which is why it becomes lighter. It's all about really the molecular expansion. Another characteristic of water is the fact that water is what we call somewhat inert. Now, that may be by definition not exactly correct, the fact that we're calling it inert, but it is a compound that does mix with other types of things that, as well as it will work with other types of substances. So, but either way, that's totally fine. The dissolved oxygen from that air would also encourage corrosion. The fact that when you have water and you bring in new water, you actually have some dissolved oxygen in that solution, which is one of the reasons for corrosion in a system. So when we bring in new water from, let's say, refilling a system, or you have a leak in the system, corrosion is a huge little part that we have to deal with. So that's one that we'll be careful with on that. And of course, one of the other characteristics of water is the fact that water contains minerals that can also lead to scale. Now, in a closed loop system, I don't typically expect this to be an issue. However, there are some systems where if you've got if there's enough leaking out in there, you will show signs of significant corrosion effects that are going to be in that system, especially when you're replacing all of that fluid. So any of those systems where they're using a heat exchanger, let's say an ice machine, where they may be using a coaxial coil or any type of a water-cooled type system, that could become a problem. So it is something that we worry about. Nowadays, we are very, very cognizant of the fact that water chemistry is really something that we need to concern ourselves with, just due to the corrosion inside boilers and heat exchanger failures and things like that. And a lot of that is dealing with some of the issues and the hazardous parts of the water that when we bring those in. All right. So let's take a look at a few more things that we have in here. I'm going to switch here a little bit to a highlighter. Okay. All right. So one of the things about water is the fact that water is really the main fluid, the main medium to understand that we have to circulate that through a lot of our systems. Now, we also use water in the case of, let's say, steam systems, and that's still considered a hydronic system, but it's just a different type of hydronic system where we're utilizing latent energy in the fluid. With water, we're generally always trying to utilize in a let's say a typical boiler system, which is the focus of this. We're going to be looking at it more from the standpoint that water, as it circulates through the system, we're trying to transfer sensible energy, sensible heat. So where we're seeing changes in temperature on there. So we're going to take a look at the reasoning. It is so essential to really have a great understanding of hydronic systems. It really helps to understand from a troubleshooting standpoint, from an installation standpoint, why you're doing certain types of tasks, things like that. So it's really interesting. So let's take a look at it. So I talked a little bit about sensible heat versus the latent heat. So when we, let's talk about the differences. So specifically, when we have sensible heat, when we basically absorb heat and we see that as an actual change in temperature of that material, whether it's the water temperature change from 200 to 180, that is considered a sensible heat process. That is something that we can physically measure when, generally with a thermometer. When we have latent heat, we can't identify or specifically determine that amount of energy that was released or absorbed by that changing of the phase of that substance, such as water. But what we can do is we can utilize other substances and their temperature changes, their sensible changes, if we know enough about those substances. So latent heat is not really the focus of this particular module, but it is something that is a characteristic of water. So let's take a look at one of the other characteristics of water. And one of the things is its specific heat and heat carrying capacity. Now, this chart that I show you on the right is right in here. This particular chart, normally we think of water as having a specific heat capacity of roughly 1.0. Now, as you can see, the specific gravity does change a very slight amount, as you can tell by the line that is not straight across when you change in the temperature. However, the amount of change is so minor that we just generally use 1.0 as its factor and for any type of changes. We'll look at the reasoning why. That has a lot to do with the fact of how much heat carrying capacity that water has, and we'll look more into it. We'll look also at some of these, one of the issues, such as, for example, ice has a specific heat of roughly 0.48 BTUs per pound per degree Fahrenheit, whereas comparatively to water, and you might say, well, ice is still water, but ice is actually we'll call it it's had a phase change. So it's no longer the same type of it's the same substance, but it's in a different form. So when we have that can have changes in specific heat, and that's the point I wanted to make. Steam, the same thing. So water has an accepted value that we use in the industry as 1.0 BTUs per pound per degree Fahrenheit is the way it is. So it's a very essential component of that. So let's take a look at specifically how that is. One of the characteristics, and you might say, well, why in the world would we use water? Why not? Everybody uses air, right? Well, not exactly. In a commercial job, if we had to move air throughout an entire building, those duct systems would have to be so large. So when we take a look at our commercial applications, we will utilize hydronics or water. We'll move water around through the system just primarily because of its incredible heat carrying capacity. In this example, we're looking at a 3/4 inch tube that is carrying the same amount of energy as a large 14 inch by 8 inch duct. And if you if you look at that and you see that, you can see how the more heat and the more, let's say if it's heating system, the more energy you have to carry from point A to point B. I don't need as big of a conduit to carry all this stuff. So it's really a great way to move a lot of energy in a very small space. And that's the beauty of hydronics. There's many more things as well that are pertinent to it, such as the comfort. It's incredibly comfortable with hydronic systems compared to air systems. So a lot of variations there. So it's great. Here's another characteristic that I'll hit up a little bit. One of the things about water is it has a very good specific heat, a very high specific heat. Now, if I compare that to other substances, for example, water has a specific heat of 1.0. That's 1 BTU per pound of that substance per degree Fahrenheit of change. Now, if I look at that and compare that to air, air has a specific heat that is, this is right here, air, that has a specific heat of 0.24. Now, 0.24 is it's less than a quarter of the amount of energy or heat. But the big factor here that really has a major influence on that is density. So when we start looking at density and we start looking at heat carrying capacity between these two, the water has an incredibly high amount of heat carrying capacity. It's one of the highest substances in the ability to move heat and have a great method of transfer of energy. So it's really good. All right, this little slide that we're going to go through a little bit, this is something that shows you the density change of water as we move on through a system. Now, water is one of the unique substances in the fact that its density, its actual density, is the highest at about 39.2 degrees Fahrenheit. Now, it's an unusual phenomenon that the fact that it actually starts to go lower, and we're talking minute amounts. When you go from 39 degrees down to 38, 37, and so on, the density starts to become a little bit less. And when you start to go and much warmer, you'll notice in the picture on the left side, you'll notice how as the water becomes warmer this way, you're seeing the density decrease. So the reason and why that's so important to recognize that is the fact that water will, because let's say it does get warm and we heat it up in a boiler system or a water heater, that's also, that reason in this little slide right here is exactly the reason why we end up getting thermal circulation. So that's something to be aware of in the fact that we're using methods. We have to have methods in our piping layouts and systems that will prevent that thermal circulation is one of the things that we want to look at doing. All right, so let's move on to the next one. So there is a formula that we use that describes the heat transfer of energy, and I want to go through that one a little bit in here. The textbook that you guys have goes through it a very minimal amount. I'm going to go through a little more detail in this. So when we look at the storage energy of a fluid and what goes on with its change in temps, what we look at is a base formula where the item H, what we're showing here, is the quantity of heat that we would either absorb or release in BTUs. The weight of a substance, let's say that would generally be in pounds, times the specific heat content, which is C in this picture, is taking that times the delta T, is really what we call the sensible heat equation. We can use this equation for any type of a system where we would be doing a temperature change. So if it's concrete, if it's copper, if it's air, we can use that if we know those things. Excuse me. So when we introduce that and we want to know what an hourly rate would be, we would simply have to add a rate or a fluid flow rate. So you'll notice in this this W has now changed from just pure weight to a rate of flow in pounds per hour. So everything else stayed the same, except once we added that hourly rate, now we were able to put a heat content in BTUs per hour of heat transfer. All right, moving on this next one. Now, if we look at, let's try to plug some numbers in so we understand this equation and what we're doing with this. So the BTUs per hour is one of our equations that we're looking at, and that's identified as Q times the rate of flow, specific heat, and the delta T. We have a couple of factors that I want to identify as characteristics of fluid. So generally we consider water as having a weight of around 8.33 pounds per gallon. Clearly this is going to change as the density changes, but that's kind of the given rate that we always associate with. Just as the general density of water being 62.4. Again, that is an accepted value, but it does change. So let's take a look at the next one. Now, if we take a look at the quantity of heat that we're using and we plug in the weight of the gallon of 8.33 times essentially the volume of water that we're dealing with in here times the delta T, we come up with an equation that looks a little bit like this, where the BTUs is equal to the weight per gallon times the gallons times the temperature change. Now when we do that, that allows us to determine how many BTUs of energy are we moving from point A to point B. So you'll notice that in this mechanism here, we're transferring energy and changing the water from 70 all the way to 180 in this top image. In the lower image, we're taking water and we're actually transferring that energy from, essentially you can see how we've removed the heat from the 70, and as we got rid of that heat, we have actually cooled that. So we have two situations here that I want to point out. The fact that the energy in water is very transferable. It's exchangeable. It doesn't matter whether you're going to heating or whether you're going to cooling. If a BTU that it takes to do cooling is the same as the BTUs it takes to do the heating, there is no change that would be going on in there. So that's an example of one of those situations. All right, I want to move on to this next equation here. So in this example here, we're looking at the sensibility equation and how this is manipulated a little bit to a more of a typical equation that we use in our field. And what I'm going to do is I'm going to show you this. So I took this, this BTU per hour equation, and I took that times or equaling the weight of water at 8.33 pounds per gallon times 60 minutes an hour, which is just a constant, times the specific heat content of water at 1.0. So it's 1 BTU per pound per degree Fahrenheit. And I took that quantity times let's call it the flow rate in gallons per minute right here. This would be identified as GPM times my delta T, which is in degrees Fahrenheit. So we're going to plug those numbers in there. And what it's going to do is it's going to give us a shortened equation of a number that is going to be 500 times GPM times the delta T. Now I can use that equation in any situation where I want to know what I'm transferring for energy from point A to point B, whether it's BTUs per hour cooling or BTUs per hour heating. I can do that. So this 500 is kind of let's call it somewhat of a constant, but as you can see, it was derived based upon this part of it. So if I look at the 8.33 times 1.0 times, and that's 60, this right here is going to come up to close to 500. It'll actually come out to about like 499.8, but we rounded up to 500. It's close enough for applications in the field, but it's a fantastic equation. We use it all the time in hydronics. So we can determine a number of different ways, as we said. If I want to know, hey, I want to know how many BTUs this boiler is transferring to the water, I can use that equation. There's obviously I have to know my GPM, and I have to know my delta T, or I have to know the BTUs. But if I know those, I can, any one or any two of those, I can determine the other in this case. You can also even, if you want to go a little bit more advanced, you can even go to determine the water energy or transfer of energy that could even be used in a heat exchanger for air. So this equation that's shown in this bottom picture right here, this portion of it, this one here is actually using the same types of numbers, except we're going to do it for air. So this right here side is actually going to be for air, and this would be, of course, how many cubic feet of air a minute I would move. 1.0 is a constant times the temperature change, and this is leaving air minus the entering air. So this right here will actually give me the BTUs per hour that I would be transferring from air. And then it's essentially taking this and dividing it by 500 times your delta T, and that of course will tell you your GPM. So if I essentially can go to an air handler or a unit heater or something, anything that's transferring energy to the air, I can actually use the same equation to determine what am I doing for BTUs per hour. And then this side, this whole equation here has to stay in the denominator of this equation, and that will tell us what we have for flow rate in gallons per minute. Another one of the characteristics that we'll hit up on with water is the fact that water has some dissolved air. Now earlier, in one of the earlier slides, I had mentioned that water is a problem where water will actually create some corrosion, and it can do that when it's in contact with ferrous metal type components such as iron, steel, things like that. So it's something that we have to definitely take a look at. And in every design of a hydronic system, you want to make sure you have some way to get rid of that dissolved air. And some of the ways that we generally will do this is we'll try to either heat the water up, or we'll try to use some sort of like a micro air bubble scrubber that will allow us to do that at a fairly good rate. Another one of its characteristics is the water is somewhat incompressible. When we are trying to put water and we try to pressurize water, we're actually not really changing its volume. And that's a good characteristic. Now, generally speaking, water can contain some dissolved oxygen that would be in that fluid, but that's not really compressible. If you have air bubbles that are in the system, now that would be somewhat compressible. But pure water is not really incompressible. So why do I care about that? Well, one of the reasons why I care about that is that tells me that if I'm moving water through a system where when the water that, let's say if I leave a boiler at 5, 10, 15 gallons a minute, that also means that that's also the water flow rate coming into the boiler. So we'll look at another picture and another example. So in my example here, this is just a little bit of an identification of looking at point A. So if I look at point A, I know that I'm moving fluid into here. So whatever that flow rate is there, that's exactly what that flow rate is also here. And whatever flow rate would be going in here is also the flow rate that's going in here. So essentially, that right there tells me that anywhere within a single circuit that is common to multiple circuits, I can identify what that flow rate is no matter where I am within that circuit. So whether I do it on the return or the supply, it really won't matter. All right, so let's take a look at the next area. And the next area is going to discuss static head. And this is really kind of pressure. When your textbook talks a little bit about pressure and exactly how we figure that out in a system. Now, this is something that's absolutely imperative to understanding, why you set systems at certain pressures and why you set the fill valve at a certain pressure, and maybe why you pump air pressure into a compression tank that might be a certain pressure. So let's take a look at that. So one of the characteristics of water, and your textbook even talks a little bit about this, is that we will look at the pressure or the head of a system as roughly having about 0.433 psi per foot. And that's strictly due to elevation, due to height. And of course, that equates to roughly around 2.307, or a lot of times we'll just round it up to 2.31 feet of water per psi. So what do we do with that? So what it tells me is that if every single 2.31 feet of water that I have, that's going to equate to essentially 1 psi. Every time I go up, another 2.31, and so on and so forth. So in this example, when I'm looking at a 10-foot column of water, that will yield me at 10 times 0.433 psi, which would give me about 4.33 psi. Now the assumption here is that up on the top of this, that would become 0, up at the very top. So, and we'll look at more of that. Shape doesn't really matter either. So static head is really related to the height, and strictly the height. So let's take a look at this. Now in my example here, I've got a skinny little tube, and it's showing the same 4.33 psi. I've got a bigger tube. So let's say if this is, maybe this one here happens to be a 1-inch copper tube, and this one here happens to be, let's say, a 10-inch steel pipe. It doesn't matter what the size or diameter is. It's the same. The pressure is the same. It is purely a function of height relative to the pressure on that system. This is one of them. This is another one. Even the shape. The other two were nice little straight vertical sections. And, whoops, I'm trying to get that to go. This one here, you can see it's got a real funny shape to it. Doesn't matter. It's purely height. So that's a very important characteristic to understand about water and pressure. So this next one here, I want to look at this. Now we talked about shape doesn't matter and so on and so forth, but the head does, the static does. So in this top one, you'll notice that I'm at 0. I went down 10 feet, and you'll notice how my pressure went up to 4.33 psi. I even added another 10 feet of height on top of that, and all of a sudden now I'm up to another 4.33. So that total comes out to about 8.66 psi. Now, for this single reason, this is exactly the reason of how taller buildings and systems that have higher hydronic systems that have bigger, not so much larger pipes, but taller pipes. Those systems generally have more pressure and they require more pressure. This same concept is also the reason why a water tower is way the heck up in the air. That is exactly how our systems maintain its pressure in a let's say in a residential open system where you're not, it's not a closed system, it's an actual open system. So, and again, pressure we know increases, they're proportional to the height, and this is an example and just another view of this. Now, what I want to show you in this example is here's a system where I have air pressure on the top of the system that I'm putting in, but I'm putting it in at 5 psi. Now that 5 psi of air essentially takes the height of the fluid. In this case, we're dealing with 20 feet of height, and we are starting at 5 psi. Right here, we're starting at 5 psi. Now, once that water starts to go, we're starting at 5 here, then everything else beyond here is going to add another, what's this, what's the elevation head, the static head due to that elevation? Well, the 5 is the initial head plus the 4.33, which would give you 9.33 psi at that point in the system. Now, everything that I add beyond that, same thing applies. We're going to add another 4.33 psi for a total of 13.66 psi. So in this system, where I am starting at 5 psi within my system, regardless of whether it's air or whether it's water, it doesn't matter. What determines the actual pressure you would measure on a system, on a hydronic system, is dependent upon what is the pressure at the top of the system and how much height do we have from that point down to the bottom of the system. And that's what's going to determine the amount of pressure that you would have. So that's really kind of the significance of why we have systems that aren't maybe maybe you have a system that's only 10 feet tall, and this system has a pressure on it that's 15, 16 psi. Well, it's because somebody started, or we started at a higher pressure in the very top of my system is what caused that to happen. All right. So this is just a little bit of a recap that your textbook talks a little bit about, and it's showing us the same type of concepts where water is relative, the pressure is relative to the height difference in there, and that's primarily what they end up using on there to solve that. Let's take a look at another some of the other areas of head within this system. So we've been talking a little bit about really kind of pressure head, elevation head a little bit. We called it static head a little bit, and so let's talk about this a little bit. So first thing I want to hit up on is the pressure head is essentially it's the amount of energy that you have in that substance because of its pressure. So that would be, let's call it relative to the 5 psi in the previous picture. That was what we would call pressure head. Now the velocity head would be how much energy are we putting into that fluid because we're moving that fluid, because of its velocity of the fluid. That's generally a fairly small amount. We don't anticipate a lot of that velocity head to be in that substance. Elevation head is really because of its height, and that was, so every time we changed from another 10 feet, we added another 4.33 psi. That is as a result of elevation head. The total head that we actually generally measure in a system is really the sum of all of those. So let's take a look at an example. Now in my picture that I'm showing you here, we happen to have, let's see if we can get my pen to change. Okay, and I'll do it this way. Okay, so my static head in this system should be 10. My elevation head is really the 65 feet. So what we're going to do is I'm going to show you how to figure that out. So it's actually going to be 65 feet, and we're going to take that times, to figure out my PSI, we're going to figure every 1 PSI is equivalent to 2.31 feet. Now the textbook in your book may have used 2.307. You can do it this way, and that will determine your system pressure, what that would end up being. And we're going to get the calculator out. Whoops. So my calculator is going to come up with 65 times 1 divided by, of course, 2.31. And I'm going to come up with roughly around 28.1 psi. Now, I'm going to give you an alternative method to do on this. The alternative method would be taking the 65 feet, and that would multiply that times 0.433, which is the number of, let's call it PSI per foot. is what that would be. And when I do that, 65 times 0.433, you'll get roughly 28.1. And that would be, of course, in feet, or excuse me, in PSI of pressure. So that means this is 28.1 PSI. This is 10 PSI. And of course, the velocity or movement ahead, as I said, is normally very minimal. If we were moving a little bit of water in there, that might contribute a little bit, but very, very minimal. This is usually something I don't even worry about. So my total head in pressure is actually going to be 38.1 PSI in this system. Now, we sometimes are concerned about the PSI on the system, but that is actually convertible to, let's say, feet of water. So I can convert this, and I need to do this for hydronics, and the fact that I'm going to take that, let's call it the 38.1 PSI, and I'm actually going to convert that over to feet of water. And when I do that, I'm going to take that times 2, I'm going to multiply that by 2.31 feet per PSI. So when I do that, that's going to come up to 38.1 times 2.31, and you're going to come up with to approximately about 88 feet of water. It's approximately, okay, 88.011, and that's even approximate, and that's feet of, we call that sometimes feet of water or feet of head or water column, however you want to say that. But that's really what that pressure ends up being. So it's a good good skill to know how to convert those. So what do we do with this? All right, so one of the things that I need to recognize is that the pressure does change due to fluid movement. So in my picture that I'm going to show you here, there's two ways that this is done. One of the ways is we could put a pump within a system, a circulating pump, and we could take and move fluid in a system, and maybe the pressure going into this pump happens to be 10 PSI. The pressure in leaving that pump would be higher in this case. And most of us would say, well, that's pretty obvious, pretty easy. But that pump is actually adding what we call head. It's adding pressure to the fluid. And that's due to the energy that was transferred into that pump to change as we change its head. We also have substances that actually remove pressure. And we call these, resistance devices. So for example, I might have a valve, or I could have a heat exchanger or piping or whatever that might be. If we know that for a fact that when we move fluid in a system that is not changing elevation, we know that there will be pressure decreases in that system. Just as if I went up in the piping system that would vertically up, I would lose pressure due to the elevation head. So that's really one of the types of changes that we have to understand on here. So in this picture, we are taking water at 18 PSI, and as we go through this resistive device, we lose some of that head, and that's a pressure drop. No different than when I have air moving through a duct system, and the pressure starts the highest at the discharge of a fan. By the time it gets through the outlet, we have already lost some pressure, and that's the same type of concept. This image here also shows us about this vicious friction, this head loss that we're losing, this either gain or loss of energy. And when we do this, when we look at a system, I can go to just about any system and measure its pressure at one point in a system. So let's say at 15 PSI at this entry point here. And as I travel and move fluid through these piping systems for X amount of feet of piping, I will see actual losses in pressure. That is due to the frictional resistances of those piping systems, such as typical things that can do this would be like valves, or you can have that by the actual just the resistance of the piping itself. That can do that as well. So that's something else that we understand. All right, so this isn't exactly what you think. This is a Ferris wheel. We're not going on our little ride, but this is a great demonstration to show really what happens in a Ferris wheel. So when we have a closed loop system, such as in this figure A that's shown in here, and I'm going to change my color of my pen. Okay, so when we have fluid that is in a piping system, we're moving up through this system. As we start here, we are at the highest pressure right there. It is the highest pressure. As I travel upward, I am losing head due to the resistance of the piping as well as the going vertically up. Every time I go up 2.31 feet, I lose another PSI purely due to the elevation head. Now, you might say, well, okay, what does this have to do with anything? Well, as I travel through, as I'm going up vertically, I'm actually losing head due to the elevation. Here in this horizontal section, I'm actually seeing the pressure decrease, but not due to elevation, but purely due to resistance. As I travel down, I'm losing pressure due to the resistance, but I'm also gaining the pressure. I'm gaining pressure due to the elevation head. So in this case, what I'm telling you is that you lose pressure when you go vertically up, but you gain pressure as you go vertically down. So what these are is negating factors. They overcome each other. They independently will be able to cancel each other out. Now, why is this important? So let's look at the Ferris wheel analogy here. So if I were to take and put equal weighted people in every one of these carts, every single cart, every one of these carts, if I put equal one of those, all I would have to do, the motor that drives this Ferris wheel, okay, I'm going to put a little belt on this thing, and here's my little motor. The motor on this little Ferris wheel would simply have to just rotate this Ferris wheel and overcome the resistance of just the bearings and the initial inertia, let's call it, it has to overcome. When I take a look at that, that's pretty easy, okay? I don't have to worry about the weight of the fluid. I don't have to worry about any of those things because everybody's the same weight and they all cancel each other out. So in a hydronic system, my circulating pump doesn't really care on a closed loop system what the height of the system is. It is completely irrelevant. All it cares about is what is the resistance of the actual piping system, and whatever vertical increase I go up, as long as I have a closed loop system, I have nothing to worry about, and elevation head becomes a non-issue. So in a closed loop system, all that really determines or matters on the fluid, on the resistance that the pump has to overcome, is really just due to what we call the vicious friction. It's the frictional loss that goes on in a system. That's all you have to compensate for. In electrical systems, Ohm's law was very proportional. It was a straight 1-to-1 ratio. When we look at the resistance of a system, it's an actual squared relationship. So it's an actual curvature. We'll look at this in a little more detail on there that relates to how we recognize if we're going to double flows or quadruple flows, what happens to its resistance, and is it realistically even achievable? We have another little way of determining resistance in a system, and one of its pressure loss devices that we look at and we use in hydronics is that we use the thing called flow coefficient, or CV factor. And when you're selecting control valves in our field in hydronics, we actually pick control valves that will either have high CVs or low CVs, depending on what we're trying to do. There's an actual right or wrong way to do this. And the CV factor is actually defined as an actual flow rate in gallons a minute that you would get across a component or a valve at a pressure drop of 1 psi, or you could say 2.31. And the reason is because these are equivalent to each other. 1 psi is also equivalent to 2.31 feet. So we have to, that's something that's a little bit more of an advanced topic. We won't get into that too much, but it basically is something that we do need to look at that in hydronics. All right, so in your textbook, they also talk a little bit about pressure drop and how that is important in a hydronic system, and it absolutely is. And the pressure drop in a hydronic system is something that we measure in hydronics to tell us, essentially have us give some understanding of what our flow rate might be. And so I want to use the example up on top. Is we have a flow rate on this top system that happens to be 5 gallons a minute, and the pressure drop that we measure across the component has a delta P that is equal to 5 psi. Okay, now I want to show you this. So we got 5 psi of drop differential. We'll sometimes put PSID. And whoops. And when we look at this picture down below here, you'll notice that we doubled the flow rate. And when we double the flow rate to 10 gallons a minute, what happens is we end up getting a resulting change where the pressure drop is actually a square of the change in flow rate. Now, let me show you what I mean by that. So the way the numbers look is when we take 10 GPM, which is what I had as the after flow rate, and we take that and divide that by the initial flow rate of 5. That's 10 divided by 5, which will be 2. This quantity is squared, okay? And that square ends up being 2 squared, which is where the 4 is coming in. We take that 4 times the original 5 psi, which is the resistance at the 5 gallons a minute. When we take that, it ends up being 2 squared times, which is 4, times 5, yielding you an expected pressure drop across the component that's equal to 4 times the initial pressure of, so that would be 20 psi. So this is something that you definitely need to recognize. Now let's specifically put that into meaning. The chances of me being able to say to go to a system and with maybe a specific pump you might have and say, you know what, I'm going to double the flow rate in this system, it's almost impossible, because that would mean that my circulating pump, which is overcoming this resistance, would actually need to quadruple the initial pressure drop. Now, that is difficult to do in a lot of systems. We might be able to go up by 10 or 20%, but doubling the flow or tripling the flow is difficult without doing additional types of changes in pumps or piping and things like that. All right, so a quick little review. How many BTUs are required to raise the temperature of a half a pound of water by 2 degrees Fahrenheit? Now, if we use the initial equation of 0.5 pounds of water, which is the weight of the fluid, times the specific gravity of 1, so we're going to take 0.5 times the specific heat content of water, which is 1.0, times the temperature change of 2 degrees Fahrenheit, which is the delta T. That right there, 0.5 times 2, this should end up being 1 BTU that we'll end up having. And of course, that is indeed the answer. When we look at the next question, it says, how much pressure will a column of water that's 1 foot high exert? Now remember the equivalent. every 2.31 feet you had a PSI. Well, if we took that and divide that out, it'll actually come out to 0.43 PSI. That is one of my conversion or equivalents. So this is a good one for you to remember. A foot is equal to 0.433.